Studies on a population are often performed on smaller subsets of the population because a subset, or sample, is quicker and cheaper to access. The population might be Year 12 students in all of Australia, dingoes in eastern Queensland, or red kangaroos. A well-chosen subset of the population called a sample will give useful information about this population. How to select the sample then becomes important, and it's a measurable feature. To make valid conclusions about the population from the sample needs to have a similar nature to the population. A simple random sample, for example, gives every member of the population an equally likely chance of being selected. If a proportion P of a population has a particular attribute, then the proportion of a simple random sample with the same attribute is denoted by a P with a hat on top. So we call that P hat. So let's try an example. In a random sample of 100 homes, 22 were found to have central heating. What proportion of homes from this sample have central heating? So that would be denoted by P hat. And what does this tell us about the proportion of homes with central heating in the greater population? So to answer this question, let's illustrate what it might look like. Imagine that the entire population of homes was contained within that circle. Now I take a random sample of 100 homes out of that circle. So I randomly select 100 homes. That's not 100, but I'm going to pretend it is. And put that in my sample of 100 homes. Now in that sample of 100 homes, 22 have central heating. So P hat equals my sample proportion, 22 over 100, which is 0.22 or 22%. What does this tell us about the proportion of homes with central heating in the greater population? P hat equals 0.22. That's our sample proportion. If I were to take another sample of another 100 homes, and I'll denote that sample by triangles. So within the greater population, I'm randomly selecting another 100 homes, and I'll put those in this triangle. So this is now sample in this second sample. It might be that 25 homes have central heating, in which case the sample proportion would be 25 over 100, or 0.25. So with two different samples, random samples, taken from the same greater population, results in two different sample proportions. It follows that the sample proportions of greater populations are randomly distributed variables with a mean equal to the greater population. The mean denoted by mu equals P, the proportion of the greater population. And the standard deviation of the sample proportions, sigma, will equal P times 1 minus P over N in the square root of that term. Hence, by the 68, 95, 99.7% rule, which was discussed for normal distributions in Chapter 14, 68% of the sample proportions will fall between P plus or minus the square root of P times 1 minus P all over N. So this term represents the standard deviation, sigma, of the distribution of sample proportions taken from a greater population. And P represents the proportion of the greater population. So to answer the question above, what does this indicate? tell us about the proportion of homes with central heating in the greater population P? It doesn't. The answer, P hat equals 0.22, gives us one solution. So the sample proportion for one random sample from the greater population. Okay, so let's try another example. Okay, assume that 60% of people have a driver's license. Using a normal approximation, find the approximate probability that in a randomly selected sample size of 200, more than 65% of the people will have a driver's license. So let's think about this problem. We've got a population, and in that population, P will equal 0.60. So we're given that information because they are telling us in the greater population, the proportion of people with a driver's license is 60%. Then they say, assume you take a sample size of 200. Calculate the probability that more than 65% of the people will have a driver's license. So that means we randomly select, say, 200 people, sample size of 200. So in our sample size of 200, what is the probability that the proportion will be more than 65%, greater than 0.65? To calculate this, recall that the sample proportion, P hat, is the population proportion plus or minus the standard deviation of the population proportion times 1 minus P all over the size of the sample. So the standard deviation is this term here. We'll solve that first. The standard deviation is the square root of 0.60 onto 1 minus 0.60 all over 200. And that equals, standard deviation equals 0.0346. And the average sample proportion, mu, will equal the greater population proportion, which was 0.60. So what that looks like on a normal distribution curve is the average sample proportion is 0.60, and one standard deviation away would be 0.6346, and one standard deviation to the left would be 0.5653. 0.5654, accurate to 4 decimal places. So this area here would be, there is a 68% of the sample proportions would fall within this range, 0.6 plus or minus 0.0346. But the question is asking, what is the probability that a sample proportion will be more than 0.65? So more than 0.65 is out here, say approximately there. So if that is 0.65, the question is asking, what is the probability that the sample proportion will lie in the right tail of the standard normal distribution curve? Now, to solve this problem using tables, the tables are defined using the area under the normal distribution curve to the left. So what you would have to do is you would have to calculate your Z-score In a graphics calculator, it's much more direct. And in a graphics calculator, when you enter the standard deviation, the value for the standard deviation of 0.0346, you would enter the mean, which is 0.60. You would enter an upper bound, being a very large number, equal to, say, 10 to the 10, and a lower boundary equal to 0.65. And what that would do in the graphics calculator is that would then calculate the area under the normal distribution curve to the right of 0.65. And in a graphics calculator, that returns 0.074. So the answer is, the probability is 0.074 or 7.4%. Let's solve the problem using Z-score tables. So we know the average, so using Z-score tables. Z-score equals x minus the average all over the standard deviation. X equals 0.65, our sample proportion, minus the average, which is the greater population proportion, which is 0.60, all over the standard deviation, which we calculated above to equal 0.0346. That equals 1.4451. And that is our Z-score. So we go into the tables, and in our tables, we get a Z-score of 1.4, and then we read across, and in the tables, when we read across, it starts with 0.00, 0.01, 0.02, 0.03, 0.04. The tables are only accurate to the hundredths spot, decimal point. So we find the area under the curve, which corresponds to 1.44, which is this value here, which ends up being in our table 0.9251. Now remember, in our tables, we are actually calculating the area to the left of the Z-score. So the probability that the sample proportion is greater than 0.65 equals 1 minus the probability that the sample proportion is less than 0.65. Now this uses the identity from chapter 14 that the probability that variable x equals x equals the probability of the corresponding Z-score. That was an identity we talked about in chapter 14. So recall the probability that x equals x equals the probability that z equals z. Okay? Just recall. This probability here is the probability Okay. And that equals 1 minus 0.9251, which equals 0.0749. Now you compare that to the value in our graphics calculator. Our graphics calculator calculated 7.4% chance that more than 65% of people have a driver's license in a randomly selected sample of 200 people. And using the tables, we get a probability of 0.0749, which is 7.49%. Okay?